Hello, good evening everyone. Welcome to the course of structural biology and which is being offered by NPTEL and welcome to the week 6 discussions on the course of structural biology. So till now what we have covered in the previous weeks is a little bit introduction about what is structural biology. Then we have gone through the different techniques which can actually help us to give us the initial inputs of the structural biology like protein production using cloning, molecular cloning approaches. And then we have also talked about that there are three different techniques, mostly nowadays experimental techniques, to determine the three-dimensional structure of a protein or any complex and in higher resolutions. So those are the X-ray NMR, and cryo-EM. So in last 2 weeks, we have discussed little bit about the X-ray crystallography, and some of the parts were left in the last class because I couldn't complete it because of this time constraint. So I would like to start today's discussion by actually finishing the X-ray crystallography part that is left. Means I am giving you a summary. So which whenever you find any difficulty, you are free to ask me, and I will be happy to answer your questions. Okay, so so the first thing is that where we left last session is that we were going through the different means the different the theories which actually came across to understand X-ray crystallography as a whole. Means how X-ray crystallography is occurring and what are the different basics. As I if you remembered, I discussed that the X-rays are coming and hitting into the crystal, and from the crystal the diffracting rays are falling into a detector, and from the detector we actually get electron densities of the different atoms which is constituting the object that we are imaging or that we want the three-dimensional structure. But these electron densities which are being formed, or the diffraction which occurs, the diffraction occurs in a reciprocal space, or it is also known as in a reflecting plane. That is, this reciprocal space is not connected to the real space, but the information of the atoms, all the coordinates that we get, that is in the reciprocal space. And from the reciprocal space you do some, the computer does some calculations, just like the we get the structure factor, as you remember, from the reciprocal space. And the structure factor equation, when we actually do a reverse Fourier transform, we actually get into the electron densities which is required by us to solve the structure. Okay, so we also discussed that just like the means real space, which where we have the a b c as the basis vectors, so to define the reciprocal space we have something called as Miller indices. So we also discussed that how we can calculate the Miller indices from the real space. We talked about how these lattice planes, when they cut the basis vectors like a b c, and if you take the intercept and do a reciprocal of it, take the LCM and multiply that reciprocals with those LCM, you will get into that H, K and L value, which are the Miller indices. We have also talked about the different conditions, since we said that the X-ray is a electromagnetic wave, so it will have a constructive as well as a destructive interference, and to get the electron densities we require the constructive interference to occur. So what are the different conditions? We talked about Law's conditions as well as the Bragg's law. So where we saw that theoretically they showed the same thing. These laws, conditions, and Bragg's law, they are interconnected and they are pointing towards the same mathematical knowledge, but to different approaches, through different approaches. So another thing we will learn today, Ewald's sphere. So he also tried to show the means the conditions which this phenomena need to satisfy so that we can get the constructive interference. Um, okay, so yeah, so I was just starting the today's lecture, Anjali, because others have not joined. So yeah, so first of all, hello, hello, hello. Okay, so sorry that today I had an important means I was working, so this I was 15 minutes late. So yeah, you those who are watching the video and who has missed today's class, I am extremely sorry for that. So you can watch this video and I will be maintaining the time from the next week. So there will not be any delay. So you will be actually means able to see this video. Please watch this video, and then if you have any doubts, please feel free to ask me in the next session. Okay, so yeah, so uh, uh, what I was going through is that in the X-ray crystallography we have this means lattice planes which are cutting this real axis, and we got this HKL values. So just like the real space, in the real space we define the crystal by a lattice, as we discussed in the last class. And but in the reciprocal space, these HKLs, which will be actually, if you take the combinations of different HKL, then they will be forming different planes, because HKL has three axes, means three axes just like XYZ, and a point in between those axes will be falling in some plane. Okay, so all those lattice planes will be forming a lattice which is known as the reciprocal lattice. So in the reciprocal lattice, just like if you remember, we talked about the scattering vector in the means when we were talking about the scattering by two electrons, and we defined in the Bragg's law that this the scattering vector, the diffracting scattering vector, its magnitude is similar to 1 by d, and d is the distance between the lattice planes in one set of planes. Okay, so d is the distance between two lattice planes in the real space. Okay, and the scattering vector magnitude is 1 by d. Now, if you take this scattering vector as a function of this HKL in the reciprocal space, then and construct three vectors like this S and construct three planes. One of them is S100, S010, and S001. So these three will form together a lattice plane, or these three lattice planes will be forming something known as this reciprocal lattice. And this reciprocal lattice is actually perpendicular to the real axis or the real lattice. Okay, so this reciprocal plane is perpendicular, or this reciprocal plane is also known as the reflecting plane, from where you get the idea of the diffraction data, and you actually calculate the electron densities by doing a reverse Fourier transform. And so this reciprocal plane is perpendicular to your original real plane. Okay, so that we have seen also in the last class, and we will be also seeing when we are discussing about the eval sphere in the next slide. Okay, so this so since this a and a star, so all these vectors, these are some basis vectors, like S100 is some basis vector, S010 is a basis vector, as well as S001 is a basis vector. Just like for xyz, you have some basis vector having some xyz coordinates. So here these three are some basis vectors, so they are actually defined as the A star, B star, and C star. Just like the real space basis vectors A, B, C, reciprocal lattice have three basis vectors A star, B star, and C star. And since all these three axes like A star is perpendicular to A, if you take a dot product of it, that is A dot A star, you will get H, which is the value is 1, because here from this dot product also you see the value of H is 1. So that's why it is 100. And in the similar way, if you do B dot B star, which is K, that's the value will come 1, and C dot C star will be 1. So this unit vectors in the reciprocal space, they form a something known as reciprocal lattice. So why do we require this reciprocal lattice? We require this because we need to means calculate this HKL values for each points in the reciprocal plane, so that we can actually get into this scattering factor equation and use this Miller indices with the uh, with the coordinates in the reciprocal lattice to solve this scattering factor equation. If you remember, we get a scattering factor of the whole unit cell, and you will apply a Fourier transfer on it to get your electron densities. So that's why this A star, B star and C star means to define any vector. Just like if you remember, another important way to understand this is that in the real space, if you want to actually define any point, so you have some vector, okay, so that will define that point in the real space, and that space will have some coordinates like x, y and z. But unfortunately, or to make this calculation easier, we get the diffraction spots in a reflecting plane. So where you have the three, in here it was A, B and C. Okay, in the real space. So this is something known as real space. Okay, and this is your reciprocal space. Okay, reciprocal space. So here if you have some point, since we know that our diffraction spots will be forming in that reciprocal plane, so if you want to define the coordinates of any point in that reciprocal plane, which is very important to know how what are the amplitudes and how these atoms are connected to one another, so that coordinates you can define them by a vector. So this vector, just like if you want to here define some this point, you will write a vector which whose this vector will be written as, if it is a vector v, then it will be written as ax plus by plus by plus cz, right? Cz. But now you have this point in a reciprocal space, so you need some basis vector which can actually define this point in this reciprocal space. That's why we introduce this A star, B star and C star, whose means if you do a dot product with your means the original vector, since these vectors, this A star, B star and these are A star, B star and C star, this B star and this is B star and this is C star. So these are perpendicular to the real axis. So if you do a dot product, you will get 1. So any point if you need to define in a reciprocal space, that is with respect to this A star, B star and C star. So that is only written. This scattering vector is a function of HKL in the reciprocal plane. So we are defining this scattering vector with the help of this Miller indices and the basis vectors of the reciprocal plane, that is A star, B star and C star. Now, as I was discussing that one thing was left, we discussed about Lewis condition, as well as we also discussed about the Bragg's law, which are important, and only when these conditions will be satisfied, you will get a constructive interference and hence an electron density in the detector. Okay. Otherwise, there will be destructive interference and you will not be able to see the electron densities in the detectors. Okay, so another way, so as I discussed, there were two conditions, Lewis condition and Bragg. Ewald, he actually did a different take a different took a different approach where he showed geometrically what is the meaning of this reciprocal space and the real space, and what are the conditions this need to follow, the x-ray beam which is coming that needs to follow, so that the constructive interference can occur on the reciprocal plane or in the cross reciprocal lattice. As I said that this reciprocal lattice is perpendicular to the real plane, and if you draw, means if you consider this S naught, you can to construct, 1 minute. So so to construct um, so to construct this eval sphere, you can actually take these three different steps: the step 1, step 2, and step 3. So in this step 1, you can actually use this, means the wavelength of this X-ray is 1 by is lambda. Okay. So if you take the reciprocal of the wavelength of the X-ray, okay, so that will be 1 by lambda, and this scattering vector S naught, this X-ray beam which is coming and hitting the object here, so that object, this is your crystal. So imagine this as your crystal. This is your X-ray source, and this S naught is the incident X-ray beam, X-ray scattering vector which is coming and hitting this crystal. From there it will be actually doing a means it will be doing a refraction or diffraction, where this there will be a diffraction scattering vector, that is this S, and this will go, and this if you consider the length of this S naught, that is 1 by lambda. Okay, now you need to construct a sphere with this wavelength 1 by lambda, that is this Ewald sphere. And if you consider where this Ewald sphere is cutting the reciprocal lattice, and the region, if you draw a straight line through this axis, where through the axis where this S naught X-ray incident beam is coming, and it is cutting the reciprocal lattice, then you will find the origin. Okay, so construct a sphere with the origin O of the reciprocal lattice on its surface. So you have the reciprocal lattice, and if you take a straight line or you follow the trajectory of X-ray whose scattering vector length is 1 by lambda, so if you take this straight line, you will find that it is cutting somewhere in the reciprocal lattice. You take that as your origin, and you construct a sphere along this by taking 1 by lambda as your wavelength from this object. Okay, you will see that there will be another point where this uh, where this uh, uh, where this Ewald sphere is cutting the reciprocal lattice, that is this P point. If this scattering vector is going and meeting the hair or cutting or this lattice plane in the same P point, then only you will be getting this constructive interference. What I mean is that if you connect this O to this P point, you will get a S, capital S value, which is the scattering vector in your reciprocal plane. So that was being defined by this SHKL in the previous lattice vector. So this S is actually dependent on the initial S naught and S value which were present in the real space, real plane. Okay. So that is dependent on this S value is connected by S is equals to small s, that is the diffracting scattering vector minus the incident scattering vector. So if this condition holds true, then only you will be getting a you will be getting this Ewald sphere cutting this reciprocal lattice, and this P point will be following a constructive interference due to which you will get a electron density when you apply a Fourier transform on the structure factor associated with this P point. Okay, so this is this wave vector, this S, this is present in the reciprocal lattice. So this is how Ewald geometrically showed that what are the conditions that this incident X-ray need to satisfy so that you will get a constructive interference. Okay, so this is all about the Ewald sphere. Now we discussed last class, if you remember, that we have actually derived the equation of the structure factor, and we saw there that there are two different things or two important things that we need to consider to solve that structure factor. One is the means sorry. So if you calculate the density, that is the electron density rho, that is dependent upon the structure factor, the means the magnitude of the structure factor FHKL, okay, and also that is dependent on a phase, that is this alpha value alpha IHKL. So this electron density of each point is dependent on your alpha value, that is the phase, as well as the magnitude of the structure factor. Now I said that by the intensity of the points that you will get in the diffracting plane, so if we know that the intensity is equal to I is equal to this structure factor, this magnitude of this structure factor squared. Okay, so from the intensity, since you will get these spots, you will also have a intensity associated with those electron spots. So from that you can actually calculate its magnitude of the structure factor. But the phase associated with the structure factor, that is somehow lost in this process of calculation. So to know this phase, this is known as the famous phase problem, that directly if you take only a crystal and you try to diffract, and you will get only the intensities, but you don't know how one point is connected to another point in space. Because if to know this information, you need to know by what angle, if you take a reference, by what angle this point is connected to the another point in space. So that angle, that phase information is lost, and that is known as the famous phase problem. Now that for understanding more better means how what these phases are, how these phases are important. So to know that, what the people have done is that this is a very interesting experiment, that this duck, if you see, if you have a duck, and this duck, if you consider this duck is made, this duck image is made up of different waves, and each wave have an amplitude and a phase. So if you take the amplitudes of the image of the duck and take the phase associated with the image of a cat and try to means jot them together, means the phase of the cat with the amplitude of the duck, the final image that will be producing, that will be looking like a cat. Okay, so that is why these phases are so important. You have not taken the amplitudes of the waves associated with this cat image, but you have taken the phases of this cat and associated it with the amplitude of the duck. So if the amplitude were important, then the final image should be looking like a duck. But it is not the case. Instead, you get the image of looking a similar image looking like a cat. Okay, so that is why these phases are so important than the amplitude. So then people try to find out then how to calculate these phases in the X-ray crystallography, because it was leading to a huge problem for the X-ray crystallographers. So then they came out with different methods. So first there were some direct methods. So these direct methods are mostly applicable for those crystals where the atoms are much closer to one another, and there so because of that there is larger scattering by some atoms. So, means as you know that this reciprocal lattice is everything in the reciprocal lattice is inversely proportional to the things in the real space. So, in the real space, the much distant two objects are, the scattering vector in the reciprocal lattice will be much smaller. So, you can't be able to differentiate between the two scattering vectors if the atoms are far distant apart in the real space. So inversely, if the atoms are very close placed, very close to one another in the real space, just for like the salt crystals, the in the scattering vector in the reciprocal space will be much larger, and there will be some atoms which will scatter more as compared to other. And by calculating the phases of those atoms, we can actually apply a statistical approach to determine the phase of the overall system. So this is known as the direct method. But then people also found that this is mostly favorable for small crystals like salt crystals. But for protein crystals which have larger dimensions, these direct methods do not come much handy. So then people were thinking that how we can actually get the phases for the protein crystals or large crystals. Then they came to this technique of this experimental phasing, where they found that if, since we know that the scattering, the amount of scattering and also those intensities, that is dependent on the number of electrons that it atom consists of, and how these electrons are in dance or resonating with the with the X-ray photons which are falling on these crystals. Okay, so the heavy metals have large amount of electrons in their outer shells, and all those electrons are in phase or are in motion with one another, or they are vibrating in a vibrating in the same means same in the dance or same frequency with one another, so that if you use a heavy metal inside your crystal, just like in direct method you have some due to the smaller distances there were some atoms which were giving larger scatterings, just like that these heavy atoms, if they are present inside your crystal, those heavy atoms will have a larger scattering because of this all the electrons are synchronized with one another in these heavy atoms, and they have many electrons. Okay, so for that we can actually calculate the phases associated with these heavy atoms, and then use the knowledge, that knowledge, to calculate the phases associated with the other atoms in the crystal. So that is the concept of this experimental phasing. So using some heavy metal atoms or heterologous atoms in the crystal whose phases can be easily calculated. Okay, so but and how this means calculation is done, that is on basis of this Patterson function or the Patterson lattice or the Patterson space, where you can actually calculate the phases of the other atoms, where in the Patterson space, in a nutshell I am telling you that the basis vector means the distance between two heavy atoms, the or the phases of the heavy atoms, they are considered as zero, or they are considered as an origin, and the distance or this space vector between two atoms in the real in space, that is been represented by a point in the Patterson space, and there is a Patterson function from where you can actually calculate the phases of your atoms with respect to the phases of the heavy atoms. Okay, so but there is a catch here, because we know that to get a constructive interference and also all these conditions to be satisfied, and finally to get a constructive interference, we need to satisfy one thing. That needs to be satisfied is that the crystal needs to be in a perfect order, or the order of the crystal, there should be a periodicity in the crystal. Then only you will get this intensities or this constructive interference. When you are adding a heavy metal from the outside to the inside of a crystal, then it may happen that the overall means shape of the crystal or the overall arrangement of the atoms in the crystal is getting distorted. So if that is so, then the crystal, the overall orderness or the periodicity of the crystal is lost, and you will not get the high resolution X-ray diffraction means spots or the electron density spots in your in your detector. So to maintain that, people have actually used something known as isomorphous replacement. So you need to optimize your means crystal with the heavy atoms in such a way that the overall basis vector, means the size or the overall basis vectors of the ABC, they change in a periodic manner. What I mean is that if in the B direction, if a heavy atom is being imparted and the atoms are shifted by +1 unit, then in the A and C direction also it should happen the same. Means there also the atom should shift by a coordinate of +1. Means there should be an uniformity. So then only this is known as isomorphous replacement. Means you are replacing some atoms of the crystal by not distorting the unit cell size as well as the means distorting the overall orderness of the crystal. So in the isomorphous replacement, this orderness of the crystals are intact. So that is why it is known as, it is better to perform an isomorphous replacement by using these heavy atoms. Now sometimes, now this for all the atoms which are present in the crystal, we consider that this Friedel's law is satisfying for them. Means if a crystal is diffracting at a spot in the reciprocal space whose coordinates are FHKL, means the structure factor associated with that atom in the reciprocal space, if it is FHKL, the the structure factor will be equal to a point which is present in the minus HKL minus H minus K minus L point. Also the structure factor, that is this FHKL, which for ideal case, this FHKL value should be equal to this F of minus H minus A minus K and minus L. Okay, so that is the Friedel's law that we know. Okay, so that should be satisfied for an ideal crystal. But when you are imparting a heterologous atom inside the crystal, so this condition sometimes this does not happen. So there is a anomalous scattering which is, or anomalous diffraction which is going on because of these heavy atoms. So sometimes this anomalous diffraction process is also used for this calculation of these phases, which is also known as this MAD. Okay, so molecular and anomalous dispersion process. Okay, so then this isomorphous replacement, this is also known as this SIR, single isomorphous replacement, or multiple isomorphous replacement, or which is known as, and MAD, which is multiple anomalous dispersion. So these are different techniques which are experimental, which are falling under this experimental phasing, where they use a heavy atom which is an heterologous atom and to determine their phases first, and then with respect to the phases of those heavy atoms we calculate the phases of other atoms using the different functions like this Patterson functions. Okay, then you have the recent method that people mostly use today nowadays is this molecular replacement. So in the molecular replacement process, what it means is that if you are working with a protein and you know that that protein has a particular domain, and you are actually want to solve the structure of that particular domain. Now, these domains are somehow similar in two proteins. Okay, so like the IgV domain, the immunoglobulin variable domains. So there is a family known as IGSF family. So all the IgV domains will look similar to one another. So sometimes what people do is that if two protein structures are greater than 30%, means similarity is present, means greater than 30% similarity if present between two proteins, then what people do is that suppose one of the protein structure is already being solved in the PDB and that is being submitted in the PDB, and they have calculated the amplitudes and phases of that molecule, of that protein. Now we find we are working with another protein which when compared with that protein present in the database, it is showing more than 30% similarity. Then what people do is that people uses the phases of the structure that has been already submitted and which has greater than 30% similarity with our structure to solve the phases of your own structure. Okay, to solve the phases of the our own structure, we are here using the phases of some structures which has been already solved and deposited in the protein data bank. Okay, so that is we are taking the phases of those means idea taking idea from the phases of those structures which are similar to greater than 30% similarity. We are taking those help of those to make the three-dimensional structure of our protein. Okay, so that is known as the molecular replacement. But this process was not was not happening previously because, as you know, for this technique to happen, you need to solve some structures. Initially, when people started, they do not have that much structures. But now, if you see that the solving of structures is exponentially increasing nowadays, and also you have AlphaFold now, so but and also the experimental techniques have been optimized and they are forming like extracrystallography, we have a huge exponential rise in structures, so that is being solved. So now this molecular replacement method is very handy in nature to solve this space problem. So now, when you are performing this means molecular replacement and calculating these phases, now before going to the complete three-dimensional structure, what one should remember is that although we are talking that these crystals are properly ordered and these crystals will be following an ideal condition where all these conditions will be satisfied that we have discussed just few minutes ago. So but it is not always that case because there will be always some error which is associated with the data that you get. So why that is so? Sometimes what happens is that when you are actually aligning your molecule with a molecule during the molecular replacement method, using the PDB and its phases, sometimes the two molecules are not properly aligned. So that is known as this rigid body refinement. You need to rotate that rigid body or your protein by 3 degrees of proton in the 3 degrees of freedom in the translational state, that is in the x, y and z direction you need to translate it, as well as you can rotate it in 3 means the frames or 3 degrees of freedoms, so to make your protein structure aligned with the known structure and use this molecular replacement. So that is known as this rigid body refinement. Now also we know that when these x-rays are coming and hitting your crystals, so inside your crystals, as I said, for protein crystals there is 70 to 80% water or fluidic content inside your crystal. So when a x-ray is coming and hitting your crystal, so there may be some chance that your atoms in the crystal, although we think that they are fixed in one position, because of the increase in the temperature of the crystal, they may gain some kinetic energy and they can do certain displacement inside the crystal, due to which you will get some error, and that error is being defined by this B factor. So this B factor is a measure of the error which is associated by the movement or this kinetic movement of the molecules because of the increase in temperature of your crystal. So this displacement of the molecules by increasing temperature is defined by this U star U bar, and this square of this is dependent on this B factor is dependent on the directly proportional to square of this displacement of this atomic vibration, and this V factor unit is the angstrom square because this displacement unit is angstrom here. Okay, now also we talked about that in your crystal you are introducing some heterologous atoms like this heavy atoms. Okay, so now what is the guarantee? So due to which you need to see or you need to check the probability of finding the real atom or the atom which are which by which this crystal is constituted. So at the probability of finding that atom at that particular coordinate, so that is known as this occupancy factor. Whether these atoms are occupying that space in is or not, what is the probability of a particular atom to be present at a particular coordinate or a particular space in the crystal, that is known as this occupancy factor, or the way we do this refinement so that these atoms the occupancy of the atoms of the particular region is near to 1. Okay, so if everything is ideal, then the occupancy factor will be 1. So the more your data in the after doing the occupancy refinement, if it is near to 1, it is giving you a good result. Now there is another thing which is known as the R factor refinement. So as I discussed that you get something known as the structure factors from the each diffraction of atoms. So each atoms will have this structure factor which is a function of this HKL. Now, as I said, theoretically, you can calculate the structure factor from all these mathematical equations or the coordinates of the HKL by doing the indexing as we discussed in the last class. Also, I said that this structure factor can be defined by as we know that if we know the intensity experimentally, we will get these intensity values. So from there, you can actually get an idea of the structure factor because the magnitude of structure factor squared is equals to your intensity. So this is the means the magnitude of the structure factor. If you take the structure factor magnitude of the observed, means the experimental structure factor magnitude, and subtract it with the original, means the theoretical magnitude of your structure factor, you will always find there is some kind of difference between the original and the experimental, means between the theoretical and the experimental values. So how near this experimental and the theoretical values are together, that is given by this R factor. So these R factor values, if it should be near to 0. Okay, but it is never 0 because there will be always some difference between this theoretical and the experimental structure factor magnitude. So if the more it is near to 0, the more is your R factor refined. Okay, so once you do perform all these refinements using different softwares for understanding how these things are done in a more deeper context, you can look back into Sir's lectures of X-ray crystallography and you will find a wide knowledge. So after all these refinements and all those calculation of electron densities, constructing the means how these atoms are connected to one another, people get into and also finding their phases by these molecular replacement methods, and finally they get into a three-dimensional structure which they actually submit in the PDB. So in a nutshell, we have actually talked about all the basics that one should know about this X-ray crystallography techniques. Okay, so I have just tried to give you a overview of the X-ray crystallography techniques. What is the theory behind the X-ray crystallography techniques that we have discussed today. So now we are actually moving to another technique that is also a very important technique. So whoever who will watch this video later on, and if you have any doubts in the X-ray crystallography part, I will request you that you come in the next session and you ask me your doubts, because we have already completed the X-ray crystallography session. And also in each session I actually tell you that I have some practice questions, and I also leave some questions to you for your practice in home. I am sharing these slides continuously with NPTEL, and all these slides contain all those questions. So if someone of you, and also the questions have the solutions, but I will be asking you to solve those questions by yourself and then finally look into the solution. So that will actually help you. So these things that you can do in home. And if you find any difficulty in the part that we have talked till now, feel free to ask me in the next session. Okay. So we have already discussed the X-ray crystallography, and now we are going to discuss something which is known as nuclear magnetic resonance, which is also a very important technique in the field of structural biology. And this actually help you to also get very better good resolution structures, as we see for the X-ray crystallography, but they have certain differences. So if you see that there are two curves. In the top curve, this is dependent on the molecular weight of your protein. Okay. So in the first graph, if you see that as you increase the molecular weight of your protein, the most of the structures of higher molecular weight protein, that is greater than 30 kilodalton, they are being solved by the X-ray crystallography. NMR is a very good technique to solve high resolution structures only when your protein molecular weight is less than 30 kilodalton. If the much lesser the molecular weight, it will be good, much good for the NMR to give high resolution structures, 3D structures. Okay, so that's why NMR techniques were previously used by many chemists. So because in the chemical salt crystals, as we discussed, that their sizes are much smaller as we compare with the protein crystals. But nowadays, since in the proteins also, this, as you see in the molecular level, all these proteins are made up of certain chemical groups, or there is a greater chemistry associated with how they interact with one another and how they fold. Everything is dependent on this chemistry. So for lower molecular weight protein, NMR is a very good technique to provide high resolution three-dimensional images. But if you compare with the X-ray crystallography structures, amount of structures that is being solved by X-ray crystallography and NMR, you will see that within the years from 2001 to, or from 2000 to 2020, there is an exponential rise in the X-ray crystallography structures, because the X-ray crystallography structures gave very good high resolutions, and also the molecular weight constraint is not present in that X-ray crystallography. So people have used X-ray crystallography, and for now it is actually reaching a saturation point for the X-ray crystallography technique. Although I would say that you see the blue bars are not that much high of the like the yellow bars for X-ray crystallography. The blue bars are for the NMR spectroscopy. But nowadays, this NMR spectroscopy will actually is serving a different purpose, not only solving the three-dimensional structure, but also to find out the dynamics of the protein in solution. As we know that our proteins are dynamic, they are living, and in the chemical in some one chemical environment they will behave in a different way, and in another chemical environment they will behave totally in a different manner than the previous chemical environment. So all those dynamic studies of the proteins and this dynamic nature of the proteins made them is very important for their functionality. Okay, especially for some kind of enzymes. Okay, so this dynamic nature of the proteins now can be easily studied by NMR and also the MD simulations. So MD simulations we will be talking in the latter part of this course. So with the help of these two techniques, you can actually get the dynamic informations associated with the proteins. Okay, so this brings me to the differences between the NMR and extracrystallography. So, what is required in extracrystallography, as we discussed, that the major requirement of the extracrystallography is to get a three-dimensional ordered crystal. So, if you are unable to get that three-dimensional ordered crystals, then you cannot proceed with the extracrystallography technique. Similar to this X-ray crystallography, there is also another constraint which is associated with NMR. So if you will see in the next slide that all the nuclei or all the atoms which are present naturally in our body, like the carbon 12 and this nitrogen 14, this these are these atoms, this carbon 12 and nitrogen 14, these are not NMR active elements. So we need to make the protein samples with certain atoms or the elements which are NMR active. So what makes them NMR active means why this carbon 12 is not NMR active but carbon 13 or 15N is NMR active. We will discuss in the next slide. So the sample preparation, and also one thing is that while this N15 and 13C, so especially these 13C's labels are, or these 13C atoms elements are very costly because they are found in a very lesser amount in the nature, and this labeling your proteins with these 13C labels or this 15N, it takes a lot of money, or it takes a lot of time as well as money, so it is costly also. Okay, but the amount of information that it provides, so that cost can be balanced by that amount of information. Okay, so these two are the primary requirements. Then you need to, as I discussed, that for X-ray crystallography, it requires years to actually screen the conditions that will be ideal for the formation of your three-dimensional crystals. Similarly, in NMR, what you can do is that you need to actually optimize the conditions in which these labels, this as this 14th N and 12C are not NMR active. So what are the different conditions such that the labels, these 13C and 15N atoms get inserted into your protein, and that will actually help you to solve the NMR structure. So all this requires a lot of optimization, and this requires a lot of time as well. Now, for X-ray crystallography, not only the formation of the crystal is important, obviously that is the first step, but then also you need to have a higher intensity for producing X-ray source like the synchrotron to get into a higher or a larger three-dimensional, or I would say in a more high resolution structures of your proteins, you require higher intensity X-rays. So that the synchrotron or a higher intensity X-ray producing source is a primary requirement for X-ray crystallography. Similarly to that, in NMR we require high field magnets. Okay, so what is the role of those high field magnets? Wait for some time, we will be discussing in the next slides as well. Now in X-ray crystallography, we have just talked today as well as previously that we have this famous phase problem. Okay, so what is this famous phase problem? We discussed that we can easily calculate the amplitudes of the waves, but the phases of the waves in the exocrystallography, that information is somehow lost, and we just now discussed the different methods that one can actually undertake to calculate the phases. Okay, so that is the phase problem that is associated with this exocrystallography. So similar to that, in the NMR, if you see, you will get certain peaks in the NMR spectra. So those peaks will have a particular chemical shift. So wait for some time. We will be discussing what are these peaks, how these are generated, what is the science behind that, what is the chemical shift, everything today. Okay. So, but what I am giving you just an difference overview of these two techniques, two famous techniques. So in NMR, you need to actually, once you get these peaks of your proteins, where this each of the peaks is associated with each amino acids of your protein, so you need to actually assign which peak is associated with which amino acid in the protein. Then only you will be able to actually model the three-dimensional structure of the protein. So that is a primary requirement in the NMR. Then in X-ray crystallography, a larger disadvantage of X-ray crystallography is that either you get the overall all three-dimensional structure in high resolution, or you get nothing, because you need to form a high resolution or high ordered three-dimensional crystal, through which if you get the diffraction pattern, you need to solve all those phases and everything, and you get all the means overall information about the structure of the protein. But if someone is doing that and at last they cannot solve those equations and they cannot get the informations out to get the three dimension important to get the three-dimensional structure, their whole work is gone, because it is either all or none. You get every information about that structure or you get nothing. Okay, but in NMR, this is not the case. If someone is not able to solve a three-dimensional structure in NMR, by performing the NMR experiments, you generate many data which can actually help you to know the nature of that protein in that particular solution. How that protein function is happening, all those dynamic information will be associated with NMR. If you are not able to find the three-dimensional structure, still also you can get very vivid varieties of information about your protein through NMR. Okay. Now, this how you can get, because in the X-ray crystallography, your proteins are in a crystalline state. Okay, so you need to be the proteins are need to be in a crystalline state. Although you will say that this you said that last class that these protein crystals are made up of 70 to 80% of water. So then how this means why you are telling that these are in crystalline state and these are in solution state, although there is 70 to 80% water, but there is no scope of the much chemical modifications in this inside this crystal. So those water molecules are known as in crystallo state. Okay, so the proteins are present in crystallo state in the crystals, not in a complete solution state. In the NMR, you have the proteins in your complete solution, where these proteins will face a particular chemical environment due to your solvent. Okay, so that is why I am telling that NMR is mostly done in the solution, whereas the X-ray crystallography is associated with the crystalline state of your proteins. Okay. Another disadvantage of X-ray crystallography is that you can't find the protons associated with your proteins, because we said that in X-ray crystallography, what is important to get a high intensity electron density spots, what it is required that many electrons are present which are dancing together with one another, or which are resonating, vibrating together with one another, so that you get a higher intensity in the final detector. Okay, but for proton you have only a single electron, so that you can't differentiate the protons spectra with the noise which is present in the X-ray crystallography. So that's why the information or the coordinates of the protons in your three-dimensional structure is absent in the X-ray crystallography structures. Okay, but that is not the case in the NMR. we can observe most of the hydrogens which are actually associated with your three-dimensional structure. And in X-ray crystallography, there is no such limit as we discussed. There is no such limit of the molecular weight of the crystal. Whereas in NMR, you need to have a crystal which has a lower molecular weight or a smaller molecular weight. Proteins have a high resolution, give high resolution. As you increase the molecular weight of your proteins, the resolution decreases in the NMR. Okay, but means and if you compare the resolution wise the what between the NMR and X-ray crystallography, you will find that in X-ray crystallography you get much higher resolution images or higher resolution structures of your proteins in as you compare with NMR. So NMR can be 3.2.5 to 3 angstrom. Nowadays this is also getting improved. There are different techniques to improve the resolution in NMR, so it is getting improved. But if you as a gross, if you compare, X-ray crystallography structures have a higher, much higher resolution, better resolution as compared to the structures solved by NMR. Okay, and we, as I said, that this since these proteins are in an in silico in crystallo state in the X-ray crystallography technique, you get only static information of those proteins. Whereas in the NMR, your proteins are in the solution, so you can get dynamic information out of those proteins. Okay, and but another interesting thing that can't be solved for a long time by X-ray crystallography is that I said you that by solving the crystal, you need a symmetry. You need your proteins or wall formation of the crystal is also dependent on whether you have a three-dimensional fold or not. The unstructured regions or some random coils or turns, they if they are present more in your protein, then that protein is very difficult to crystallize. Okay, because it will not fit in a three-dimensional space in an ordered way. Okay, so that's why I said you that one of the strategies is to omit those areas and to form the crystal of your domains. But that is advantage of X-ray crystallography, since when omitting something, you are losing some information, right? So that information you can regain it by using NMR. So in NMR you can see the dynamic nature of these random loops and coils, and how these loops and coils are important for imparting the function of your protein. So all these things you can get in NMR. Okay, so this is an overview the advantage disadvantages associated with the NMR as compared to the X-ray crystallography technique. Now, if we now look into, if you remember that in the last slide I said you that this NMR, there are certain atoms which are or elements which are NMR active, and there are some atoms which are NMR inactive. Now, one of the means from the name only, so you must have the question that why some atoms are NMR active and why some atoms are NMR inactive. Okay, so to understand that, first let us start with the name of this technique, that is nuclear magnetic resonance. So it is somehow related to the nuclei of the atoms. So just like in X-ray crystallography, these were the electrons which were as very important to give you this electron density patterns. In NMR, it is the nuclei on which your means this NMR works. So there is a nuclear magnetic resonance. So there is something from this name you can associate that there is a nuclei on which we are applying some magnetic field, due to which we are actually there is a resonance somehow between this molecule and this external magnetic field and the energies that we are giving, such that we are getting certain information out of this phenomena which can actually help us to get into the three-dimensional structure. So if you remember, your chemistry basics, then in a nuclei there is of an atom in a nuclei of an atom there are two things. One is your neutron, another one is your proton, and the electrons are surrounding the overall nucleus of your atom, right? So electrons are present in several orbits, and in the nucleus of the atom you have neutrons as well as protons. Now, if you remember that each atom can be defined by its four quantum numbers, that is, and one of the quantum numbers is this spin quantum number. So now every proton and neutron inside this nucleus have a spin quantum number associated with it. So normally we know the spin can be plus half or minus half, right? So if you remember the basics of your chemistry, right? It has been observed that in the nuclei, when there is an odd number of neutron or odd number of proton present, okay, then only this spin, since we know that there are this oppositely oriented spin, that is plus half, minus half, and each spin will cancel out one another to give a zero spin, right? So but if there is an asymmetry in the nucleus, means the number of neutrons is greater than this means protons, and they are in odd number, okay. So the condition is either the atom should have a odd molecular mass or an odd atomic number. If that is so, then it has been observed that this nuclei has a particular spin, because the spins will not cancel out one another, because there are odd number of atomic number as well as odd mass, which from this mass and atomic number you can calculate this atom of these protons and how many neutrons are present. So if they are in odd number present, they cannot cancel out each other's spin and cannot be zero, okay. So the net spin of the nucleus which are NMR active are non-zero. Okay, just like if you see, so the main criteria, if you can remember, either it should have an odd atomic number, either it should have a odd mass number, or it can have both odd atomic number, odd mass number. So in those cases, normally those atoms are the NMR active elements. Okay. Now, if you consider the spin quantum number as your I, okay, and now if someone asks you, just like I said, that plus half and minus half, so that we actually know that this plus and minus half spin is associated with a proton, okay. But there are two different states of the spin. One is plus half, another one is minus half. But what if it is a carbon, or it is a nitrogen, or if it is other atoms, right? So whether they have also two states or they have other states as well. So for that, to calculate that, if S is your spin quantum number or L is your spin quantum number here, so this is actually denoted by different notations in different books. Okay, so we are considering spin quantum number as L, and if you take 12 plus 1, you will get into that how many uh, spin states that atom possesses, and uh, that is associated, means that spin states have a charge internal difference or the spin quantum number of plus I to minus I. So to understand this, let us go into this table. So we can take the example of proton. So proton have a spin quantum number, that is this I value of proton is half. Now if you take 2 multiplied by half plus 1, that is 2. So two spin states are present for the proton, that is plus I to minus I, that is plus half to minus half. Okay, so that is plus half and minus half. So those two are the spin states of your proton. Now if you take a deuterium which has a even atomic number, whereas the and sorry, so it has the even mass number but atomic number is odd. So since either atomic number should be odd or either mass number should be odd, so this will be also never active. But if you calculate the spin quantum number is here 1. So 2 multiplied by 1 plus 1, that is 3. So this deuterium will have 3 spin states. But now if you calculate for 12C, 6. So 12C, that is the carbon 12 that we find in nature or in our body, with which your amino acids are made up of. Since both of them are even, 12 is also even, 6 is also even. So overall spin will calculate, spin will cancel out one another, and you will get 0 net spin quantum number, nuclear spin quantum number for 12C. So that's why you do not see any spin states for this 12C, and this 12C is NMR inactive. Okay, so this 12C is NMR inactive, right? So this is how you actually see whether an element is NMR active or not. Okay, so now we see that these atoms, this 15N and this 1H 13C, all have this half spins, half nuclear spins. Like nuclear spin quantum number for all these proton, carbon 13, and 31p, 15N, 19F, 99 silicon, all have a half spin, a nuclear spin quantum number value. Okay, and we actually use these quantum numbers, these elements, to means to these elements for the calculation or for finding our structures. Okay, and also we use something known as radio frequency in the NMR spectroscopy. So why we are using this radio frequency and what is happening in NMR, we will be going into the next slide. So if you have these different nuclei in a space or in a some liquid or media, okay, you do not have any external magnetic field or anything, and you are just having these atoms present in the in a liquid or in a solvent. Okay, now since they have these spins, they can be actually forming dipoles, and these dipoles can be orienting randomly to any direction. Okay, but now when you are applying, because these are dipoles, these have a dipole, so they are also forming a magnetic field around it. So all these electromagnetic waves have two components, electric components as well as the magnetic components. So there will be a magnetic field or an electric field associated with these dipoles as well, right? But when you actually add an external magnetic field, what happens is that all these randomly oriented dipoles will now orient in two directions. It has been observed that they orient in two directions. One is parallel to the direction of the external magnetic field, another one is the anti-parallel direction in the external magnetic field. So which we define as the plus half state and the minus half state. Okay, and this plus half and minus half state, this occurs only because of this external magnetic field, and this minus half state is being said as a higher energy state, whereas this plus half state is of lower energy state, because they here this direction of the dipoles are allowing are aligning with the external magnetic field. Now, see, if you see this is a dipole, so you will have a magnetic moment associated with this dipole, okay, because of this external magnetic field. And this external magnetic field is given in a z direction. There is also x and y direction, and these dipoles which are being aligned, that is aligned with respect to the z direction, either in the means parallel to this positive z axis or parallel to the negative z axis. Now what has been observed is that there, because of this different spin states which occurs because of this external magnetic field, there is an energy difference between these two states, that is this blue color and this red color, that is plus half state and minus half state have a particular energy difference. and also this energy is written as del E, and that is this energy is dependent on the external magnetic field and the gyromagnetic ratio of that particular element or particular atom, or I would say the gyromagnetic ratio of that particular nuclei. So that gyromagnetic ratio is different for different nuclei, and it is the ratio of its magnetic moment to its angular momentum. So for each atom, for proton, it has a different gyromagnetic ratio. For nitrogen, it will have a different gyromagnetic ratio. And for every atoms, there will be different gyromagnetic ratios that will be present. Okay. And this this energy difference is defined by this formula, that is H gamma B naught by 2 pi. Now, if you consider that there are certain, so 1 minute. So here what is happening is that, um, if you consider that these two states, this plus of state and the minus of state, there is always some difference. There is a little bit difference. So if from here, let me take to this slide. So this states, this quantum states between these two, plus of state and minus of state, that can be actually means how many nuclei are following the plus half state and how many nuclei are following the negative half state. That can be calculated by this Boltzmann's equation, and yeah, here you can actually get the idea, and you will find that always for this NMR active nuclei, what happens is that there this if you take the ratio of this these nuclei which are present in the upper or high energy state to the nuclei which are present in the lower energy state, you will always find that there is some extra amount of means atoms or nuclei which are present in the lower energy state as compared to the upper. But that is very, this difference is very less, means only 1 out of 10 atoms difference are present. Means if there are means 9 atoms in the or 9 nuclei in the upper higher energy state, there will be 10 nuclei in the lower energy state. So there is only a difference of 1 nuclei between them. Okay, so that is a very small difference. But due to this small difference, what happens here is that, um, due to this small difference, there is this formation of this magnetic moment in the z direction, because this z, if you consider a moment in a space, it will have an x component, y component, as well as a z component. Okay, so three components will be present there. Now for z component, what you will find that this z component, since your external magnetic field is aligned with the z direction, so that's why what will happen is that this magnetic moment will point directly to this z direction, and in the x and y direction it will cancel out one another and it will be zero, because in the z direction only you have some difference in the nuclei. Okay, due to this difference in these two states, there we are getting an external magnetic moment in the z direction, right? So that is, this is very important. So this tell us that these conditions to satisfy that your magnetic moment should be always aligned to the z direction, you should have this scenario where there is a difference between these two two sets of nucleus, and that will only happen if you have a external magnetic field. And now if you are giving an external energy which is similar to the energy gap between these two plus half and minus half state, then what will happen is that this extra amount of population which was present in the lower energy state, it will try to go to the higher energy state. So that is this frequency, but this gap of this energy barrier between these two is very less, because the population difference between these two is very less. So the energy barrier between these two states is very less, and the energy is less means the wavelength is largest. Now, for this is why we actually use a radio frequency source. Since this energy between these two states is very less, if you use a radio frequency source which has a longer wavelength, thus have a smaller energy, and if that energy is resonating with the energy barrier between these two states, then you will get a resonance, and this extra populations will be going to the higher energy states. Okay, so that is the rationale behind using this radio frequency pulse. Now, how to use this radio frequency pulse here? This radio frequency pulse is being used at a direction 90-degree to the direction of the external magnetic field. So what happens here is that when you are giving an external magnetic field, as I said, because of this difference in the populations of the two, there is a magnetic moment pointing towards the z direction parallel to the B magnetic field, external magnetic field, right? So there is always this pointing towards the z direction. Now, when you apply a 90-degree radio frequency pulse, since this is a electromagnetic wave, it will, if you curl the direction of your electric field is like this in this x axis. Now, if you remember that around that XX means electric field, there will be generation of a magnetic field. And what will be the direction of the magnetic field? If you put your thumb in this direction and try to curl your fingers, you will see that it will fall. The direction of the magnetic field is like this. Okay, means the direction of the magnetic field here will be like this. Okay, so this generation of this there is always external magnetic field present, otherwise this magnetic moment in the z direction will not be formed. So that should be constant, but when you are using a radio frequency pulse which is perpendicular to the external magnetic field, it will generate a magnetic field B, which will actually help in this z magnetic the magnetic moment which was previously pointing towards the z direction, it will now change its direction and fall into this xy plane. Now after some time what we will do is that we will remove this 90-degree radio frequency pulse. Now as you remove this 90-degree frequency pulse, now what it happens is that since this magnetic moment and this external magnetic moment is always on, so now this magnetic moment will try to precise in this direction, because this perpendicular magnetic field is gone, and this magnetic field will create an electric field perpendicular in this direction. So this magnetic moment will be now precising in this xy axis. Okay, but this precision is not always that this will precise in this xy axis all the time, because whenever this is a moment which is precising in a circular path, it loses certain energy. So if you see, so this is going up, and from there it is actually the energy, that there is some emission, it will be again trying to come to the lower energy state. So that is comparable with what is happening here. So it will again try to go to the original position, but how it will go, it will be traveling through a spiral path whenever this 90-degree pulse is lifted, and there will be a always decay of this magnetic moment as it precise through this xy axis and go to this z axis. So that is known as this that is this free induction decay. So you have two detectors in this y direction and x direction, where you actually detect the free induction decay of this magnetic moment in both this x and y directions. Okay, and you get the decay, the energy decay is calculated in the form of these waves, which are known as this induction decay waves, and this is dependent on this time, the delay time that you are giving. So you calculate this delay time, and you the time that it requires to precede and come to the z axis to its original position. You get that time, and you plot a curve with the energy loss of this magnetic moment during this travel. Okay, so you get this free induction decay. But now you imagine that you have so many atoms present, and there will be so many free induction decays. And if you want to analyze this free induction decay and go into your three-dimensional structure, it will be very difficult. So that's why what we do, we convert this time dependent variable to a frequency dependent variable, and that can be easily done with the help of Fourier transform. So for each free induction decay, you are getting a particular frequency, which is by solving this free induction decay, doing a Fourier transform on it, and getting this magnetic moment as a, means this decay as a particular frequency, which is given as omega. You will now learn something about the Larmor frequency. The Larmor frequency is that frequency which is through by which this vector, magnetic vector or magnetic moment is actually precising in this xy direction. And if you want to see what is this relation of this omega is the frequency which is required to get this energy barrier, cross this energy barrier. So this energy is associated with a frequency that is h nu. So this nu is this Larmor frequency. Okay. So that is the Larmor frequency, and we know that for each atom they will have a particular Larmor frequency. So if you want to see that for proton, you will be giving a particular Larmor frequency, or you will set a particular radio frequency wave which contains a particular Larmor frequency specific to proton. So then you will get a proton NMR. Then if you want now if you want to detect the nitrogen 15 in your sample, then you again have a Larmor frequency specific to this nitrogen. You apply this frequency, you get this free induction decay, and see how these nitrogen atoms are associated with one another in the crystal. So this is how you perform different kinds of NMR by just adjusting the Larmor frequency and the radio frequency pulse. Okay, so now this is what we have just talked in the last slide, and one of the important thing is that this magnet, means how much high resolution structures you will get, that is actually dependent on this magnetic strength. Okay, so this the external magnet strength. Normally for those crystals or those proteins which are very smaller in size, and also for salt crystals like which have a smaller dimension, for the low magnetic field strength, magnets are okay. But for protein crystals which have a larger size, so for that to get a resolution to very high level, you require a very high magnetic field, because this energy barrier is proportional to this external magnetic field, as you can see from this equation. Delta E is equals to H gamma B naught. So gamma you cannot change, but more you change the B naught, you more get this energy barrier, which will be actually means which will help you to differentiate between two energy barriers easily, and that will increase the resolution in a crude term. Okay, so now what we have this magnetic field strength can be defined in either their frequency or the magnetic field strength. So the magnetic field strength is defined as this Tesla, and this Tesla is connected to Gauss, which is also a unit of this defining this magnetic field strength. by 1 Tesla is equals to 10 to the power 4 Gauss. Okay, so this is how this Tesla and Gauss are connected to one another. Now you have an NMR machine. For example, this is an NMR machine. So now we know that how this what is the theory behind the NMR, but how the NMR looks like. So this is the image that of the NMR machine that we have in IIT Kharagpur in the Central Research Facility. So there we have a 600 megahertz. So you see this is a Bruker, and the magnetic field strength of this NMR is 600 megahertz. So you consider these 600 megahertz magnets if you have, and greater than that, then those type of external magnets are favorable for solving high resolution protein structures. Okay, so it has a 600 megahertz external magnetic field. Now, as I said that in NMR, what is very important is that you need a external magnet. Now, how these external magnets are being produced means which will be already always they will have a this is constant external magnetic field, because they may differ with temperature, or other fluctuations may occur, and if any fluctuation occurs in these magnets, then your whole NMR experiments is gone, right? So for that, what you need to consider very carefully is that you need some means a superconducting magnet, which will always means this is an electromagnet where it will not lose energy, and it will produce always this external magnetic field as a constant magnetic strength. Okay, so that is very important. And to maintain the superconducting nature of these coils, what is very important is that, or superconducting nature of these magnets, it is very important that we require helium, liquid helium, and nitrogen. So what I want is that you can look into that what is the role of this liquid hydrogen, liquid helium and nitrogen in NMR. Okay, so you can look into it. If you don't find, we can discuss in the next class. Then there is also a probe, through which there is this probe is an electromagnet again, it which forms this radio frequency pulses, which goes in a perpendicular direction of this external magnetic field. So these probes also have the ability to detect the free induction decays in this XY directions. And then there is this console, which will actually produce the electrical power for this radio frequency pulses that will be generating and going into this your protein samples, and so that this NMR phenomena can happen. And finally we get this free induction decays, we calculate it, Fourier transform it, all of these are done by a computer interface. So the another part of the NMR is the computer. So this is the basic NMR machine overview. Okay, so we are doing now. I will show you that how, as I said, mentioned you that we will get some certain chemical shifts from this NMR spectra, and these chemical shifts are specific for a particular chemical environment. So how you actually get these chemical shifts, we are going into that. So wait for 2 minutes. I'm coming. So we were talking about that how to get this chemical shifts out of this NMR data. Now, if you see that means if your nuclei is present in a means it's not present in some chemical environment, it is present in air or an inert region. So then the overall magnetic field that you are giving, so that can be absorbed by this nuclei itself. But if this the nuclei is in vicinity with some other atoms, or for example the electrons which are surrounding this nuclei, they also are electrons, they are moving and they are also forming an electric field, so they can actually shield the your nuclei, or there can be some other solvent molecules which can actually change the overall electric field nature, effective field of your nuclei. So if there is no chemical change in this nuclei, then it will absorb the whole magnetic field. But here it is not absorbing the whole external magnetic field that is given, because this nuclei is dependent on the, or this getting affected by the electron cloud formed by its adjacent electrons. This is due to which you will get particular shifts in the frequency. So the frequency that you are actually getting theoretically to where you should have got that frequency spike, instead of that you will get a shift. So that is known as this chemical shift. So if you consider that this atom and this molecule, and you consider there are two protons, one is attached to this oxygen molecule, another is attached to the carbon molecule. Now if this you can just see that all these are protons, but they are chemically very different from one another. How? Because this oxygen is a more electronegative element, and it will like to drive or draw more electrons towards itself. Now, if you are doing a proton NMR, meaning that you use the proton NMR specific radio frequency and the Larmor frequencies associated with it, and you are doing a proton NMR, then what you will see that these protons are much de-shielded, means these electrons are going away from it, so these protons will face a different chemical environment as compared with this, because here it has a electron cloud of this carbon which is also coming near to this proton, as well as this proton has one electron inside it. So this electron is been drawn by this electronegative element towards it, that's why it becomes less shielded, means less guarded, and this becomes more guarded. So in this way you actually get a difference in the shift frequency values for different functional groups. So those are which are less shielded. Now how to know that, means how much shift is occurring? To calculate something, calculate any shift or any difference, what you require is a reference point. So in chemicals, in chemistry, normally this methylsilane, it, since it has large four methyl groups associated with a silane molecule, so what will happen is that people actually use this tetramethylsilane as a reference, because all the protons which are present in these methyl groups in this tetramethylsilane, they are much shielded with one another, so means they are much shielded with one another. So if we can compare the other shifts or the other shifts of other elements as compared to the shielded protons, we can actually get a value or idea. So that's why the protons of this methyl carbon in this tetramethylsilane, though that their shifts has been considered as a zero chemical shift, and all those elements or all those protons which are actually becoming more shielded, they will be having a upfield shift, or they will have a shift towards the zero, or their chemical shift will be towards the zero. Whereas for those which are more de-shielded, like these protons which are associated with more electronegative elements, those their chemical shifts will be more, they are more de-shielded, their chemical shifts will be greater. as compared to those which will have a shielded by these electrons. Okay, because these electrons will create a electric field as well as a magnetic field, because electrons are moving, and which will create an electromagnetic waves, and it will also create a magnetic field. That magnetic field will oppose this magnetic field, the external magnetic field, due to which you will not, if your external magnetic field has this magnetic strength or magnetic field strength, this nuclei will not face the exact 60 megahertz means external magnetic field frequency, because there will be always a decrease due to an internal magnetic field generation by these electrons. So that's why those which do not have this shielding, they will have a larger chemical shift, but those which have a shielding, which has more shielded, they will have lesser chemical shifts. And this chemical shifts is defined by this delta value, which is shift in the hertz divided by the external magnetic field frequency in megahertz. So you will get this delta value, and this delta value is different for different functional groups if you consider the proton NMR. Okay, so this aldehyde and this carboxylic acid are most deshielded, because they are due to resonance. The electron cloud has been shifting completely shifted to from this proton to these oxygens. Okay, so that's why these carboxylic acids and these aldehydes are most deshielded among the other functional groups. Okay, now, if you consider that means what information the NMR signal, just a 1D NMR signal can give you is that, so if the number of peaks that you get in the NMR 1D spectra, you can say that by those you can say that those kind of means if you get two peaks, then only two types of different protons are being present in this structure. Now there can be different splitting of that peak, but for as a gross, you can, if you are getting two peaks, you can say that there is two kinds of protons which are present. Now, if you are seeing the location or the chemical shift value actually tells you that how much that proton is shielded or deshielded. It gives you an idea about the chemical environment. Now the intensity of these peaks will tell you that how many protons are facing the similar environment. For example, here it is CH3Br. All these three protons are facing a similar environment. That's why you get a higher intensity band here. Okay. So this intensity length will tell you that how many protons are actually facing the similar environment. And there is again a splitting. So splitting, for example, which can actually the neighboring protons can actually impact the chemical shift values or the chemical shift values of the current proton, and they can split their spectra into some smaller peaks, and that is known as the splitting. Okay, so the splitting actually tells you that how many protons are present in the nearby molecule. So for protons, if in the nearby molecule, those if for example you have CH2, so since and you are trying to calculate the chemical shift of the CH, then since the adjacent has two protons, you will have that two protons will split this the CH hydrogen into 3, that is n plus 1, the adjacent protons plus 1 splitting will be happening. Okay, so this is the n plus 1 rule. So we will be continuing this. Last first, let me discuss with you the week 5 assignments. Then if we have time, then we can discuss furthermore, or we will have certain things left which we can discuss in the next session. Okay. So I would like to discuss with you about your week 5 assignments, because already if you see the deadline of the week 5 assignment is over. So I am discussing with you these assignment questions. So the first thing is in X-ray data processing, determining the intensities each spot is termed as. So we will go through each of these questions one by one and try to solve the questions. So first one is, in X-ray data processing, determining the intensities of each spot is termed as. So if you remember last class when we were discussing about the all the kinds of plates, the MAR plates, and how these means indexings are done, means what are the different steps that you need to carry out once you get these diffraction spots. I said that first thing is to do indexing, where you will actually assign the Miller indices to each of the points. Then I said that the similar Miller indices are the similar frames, the diffraction from similar planes. You need to integrate the intensities and also means determine the intensities of each space, each spot. How you can do that? By an integrating all the planes, the intensity is present in all the electron diffraction planes. Okay, so the answer to this question will be the integrating. So in my slide only it was written. So the answer to this question will be the option B, that is this integrating. Then which of the following equality must be fulfilled for Lewis condition? Now you know that we have talked about that this Lewis condition is A dot S is equals to H, B dot S is equals to K, C dot S is equals to L. Now also we know that this capital S can be written as S minus S naught. Now, if you take the scalar of this value and try to find that what is the relation between this s small s naught small s with the Miller indices, and this value can be also taken from the example of this eval sphere, where we found that s is equals to s minus s naught. To find any point in this scattering vector which is present in this lattice plane, that should be equal to your Miller indices. So this S minus S naught will be is equals to your H value. So this, if the option A, if you take a transpose or if you take this in the left hand side, it becomes S minus S naught equals to H, which is satisfying this Lewis condition as well as the Ewald sphere condition. So the answer to this question will be option A. Okay. Then the Ewald sphere demonstrates the relationship between. Now this Ewald sphere, as I said, what are the options? The wave vector of the incident and diffracted X-ray beam. So the wave vectors are this S naught as the S. So yes, so the Ewald sphere demonstrates the relationship between them, how they should behave, so that the you get a diffraction spot in that reciprocal plane. Diffraction angle for a given reflection, so this is the diffraction angle. This 2 theta is the diffraction angle. So the Ewald sphere also talks about it. The reciprocal lattice of the crystal. So this reciprocal lattice is the basis of the Ewald sphere. So yes, so all the three options are correct. So the answer D will be the correct option. So the answer D is the correct option of the third question. Which of the following obtained the first solution the phase problem? As I said, the phase problem, the first solution was given by this experimental phasing, and they are that is been done with the help of this Patterson function. So from there, the scientist who actually did that is Arthur Lindo Patterson. So the answer to this question is A. Which of the following methods for solving phase problem require the prior knowledge of structure of a homologous protein? So direct method does not require that. MAD is this molecular anomalous dispersion, multiple anomalous dispersion. MIR is the multiple isomorphous replacement, and the molecular replacement by its name is only where you required a structure where you have more than greater than 30% similarity between these two structures, and only you can actually use this molecular replacement method to calculate the phases. So the answer of the correct of this question is D. Then we have another 5 questions in this assignment. Anomalous dispersion effect is observed in. So as we discussed that the anomalous dispersion is happened in multiple anomalous dispersion, that is this MAD, and this is a kind of technique which is comes under this experimental phasing. Okay, so in this technique, the atom's inner electrons absorb X-rays of particular wavelengths and re-emit the X-rays after a delay, including a phase shift, in all reflections known as anomalous dispersion effect. Analysis of this phase shift, which may be different from individual reflections, resulting in a solution about the phases. So, due to which this Friedel's law and all is not satisfy each other, and you can solve the phases by using this multiple anomalous dispersion. So the answer to the question, correct answer to this question is B. That is multiple anomalous dispersion. In direct method of solving phase problem, ab initio phase determination is limited to. So the ab initio phase determination of this direct method, as you can see, sir mentioned about these direct methods in his slide, and he also he's mentioned that this should be less than the phase ab initio phase determination is limited to molecules less than 1.2 angstrom. So it is much for lesser molecules or much smaller molecules, these direct methods are available. So the correct answer to this question is option C. Which of the following is not a classic heavy atom used for isomorphous signal? So this also I have taken up from Sir's slide, where he was mentioning that what are the different classic heavy atoms which can, if you replace those atoms with the atoms in your crystal, then they will form the isomorphous replacement. So there are these kind of atoms which if replace, there will be an isomorphous replacement. Now, this among all these options, the uranium is not present, and it is a very means hazardous metal as well. So, this is the correct answer. So, the D option is the correct option. Which of the following parameter can be used to search for the number of molecules? So the number of molecules can be used, means what are the following parameters. So sometimes what happens is that when you are when you have associated these heterologous atoms into the molecule, you want to calculate that how many unit cells or how many molecules are present in your crystal. For doing that, there is a coefficient known as Matthews coefficient that sir has talked about. So Matthews coefficient is the crystal volume per unit of the protein molecular weight, and it is showed that Vm bears a straightforward relationship to the fractional volume of the solvent in the crystal. So if you want to see that how much volume is occupied by the solvent in the crystal, and how much volume is associated by the your atoms in the crystals, which is much important for protein crystals because it has 70 to 80% atoms, 70 to 80% means 70 to 80% solvent inside it. So this Matthews coefficient is very handy for that. So the option to this question is correct option is C. Then in molecular replacement, how much minimum percentage sequence identity with homologue is required? As I was telling, that you need at least greater than 30% similarity between two structures to have a minimum sequence. I mean, to proceed with molecular replacement method. So the option A will be the correct answer here. So this is all what I needed to discuss with you today. What we can do is that uh, we can leave up till here, and we can continue our session from means how to calculate the different means chemical shifts of a molecule, and how to know that what is the structure of a molecule, small molecule from a chemical shift. All this we will be discussing in the means how the splitting occurs, what is the n+1 rule. All these things we will be discussing in the next session. Okay, so today I have done till this, and what you can do is that you can actually look into the different slides and all these videos, everything that I have shared with you, and you can actually come back to me with your questions in the next class. So all these things will be uploaded in this Google Drive folder, and also the YouTube the video will be uploaded, the recording of the video will be uploaded in your in my YouTube channel. Okay, so thank you for joining. You may leave.